So I'm going to present recent work that we've been doing with my co-workers Alex, Florian Lhuillier, Uli Christiansen, and Gauthier Hulot. The main aim of this work is to estimate the deep flow structure and other variables as well, but deep flow, mostly for this talk, it's going to be about flow in Earth's outer core from the available magnetic observations, which, as we know, are available only on the surface. So our goals are twofold. The first one is to understand the dynamical regime of the core. And the second one is to obtain what is called a state vector for data assimilation practice. So this is the main thing that we have in sight right now. Be able to use the data assimilation techniques that have been developed, for instance, in ocean atmospheric sciences, use them for geomagnetism. So there is one big problem that the scientists in the field have already faced for quite a long time now, which is under determination. So this is a state vector. So what is it? It's a vector that summarizes all the variables, all the fields of the model at each point of a numerical grid, say, in the spectral space. So this is what the LM stands for. P and T stand for poloidal and toroidal. That's how we decompose the vector fields. And U is the velocity field, B is the magnetic field, and C is the buoyancy anomaly field. It's a scalar, so it has only one component, no poloidal and toroidal parts. So this is done on the nodes of a numerical discrete grid, and this state vector is going to be available at each time at which we look at the system. So the typical size on nowadays numerical computations, 3D numerical computations that aim at simulating the geodynamo, the typical size is 1 million elements, while a set of magnetic observations at a given time is only 200 elements, about 200 elements. So in those 200 elements, I include the magnetic field and secular variation coefficients up to degree 8 to 13, so this number is obtained with degree 13 of a typical geomagnetic field model. So what is needed is prior information, just like in any other inverse problem that you want to solve in seismology or other deep earth sciences. So the point of this study is to use a numerical dynamo simulation as a prior. So why do we want to do that? There's been a lot of work that has been done over the last 10 years in numerical dynamo simulation field, and what has emerged are parameter space explorations and scaling relationships. They have done something which is quite nice to partially bridge the parameter gap between the models and the Earth. So as an illustration of parameter space exploration, this is a typical graph on which you have about 100 dynamo models that have been plotted in a space that is spanned by the ratio of 3 timescales of the system, the rotation period of the planet, the typical time for the advection of the magnetic field, and the typical time for the diffusion of the magnetic field. And the black symbols denote models which have a high degree of morphological similarity with the Earth, which is the cross here. So in terms of classical MHD, this number is called the magnetic Ekman number, and this number is called the magnetic Reynolds number. So this is a typical model, and this is the Earth. And what this study has done here is to quantify the morphological similarity between models and Earth, and you see that for those two models, this similarity is quite high. So what this says is that you have a good chance to have a very similar model to the Earth when these 3 timescales are in reasonable proportion with respect to the Earth counterparts. And in particular, you can match almost match the magnetic Reynolds number of the model, which means that magnetic advection and magnetic diffusion will be in the correct ratio. Where you, of course, fail is in the Ekman number, magnetic Ekman number, or any other Ekman number that you can build on the various diffusivities of the system, where you still have a big gap. But still, this is encouraging and says that the large-scale velocity field that produces the magnetic field in the model may have some similarity with what you expect in the Earth. As an example of scaling relationships that I have mentioned in the previous slide, we know now how in a typical dynamo system the magnetic field amplitude scales with the available power which is made available by the thermochemical convection occurring in the Earth's core. And we also know how to scale the time of the model in such a way that the advective time of the model will match the advective time of the Earth. So these are these two studies here. And the result is that if you look at a typical magnetic field spectrum as a function of harmonic degree energy of the magnetic field, or secular variation spectrum, you can have a good match between an average model behavior, which is in solid black here. Here, the dashed line is the previous snapshot, which happens to be a little bit below the average behavior, but you will equally well find snapshots that are above. And you can have a good match with, for instance, the behavior of the geomagnetic field in two epochs here, drawn from two models of the geomagnetic field, CM4 and chaos. So you also see differences. For instance, here, the secular variation in the model tends to have less power in the large degrees, in the small degrees, large scale, sorry, than the actual field, and we are going to come back to that later. So how are we going to use a numerical dynamo as a prior? We are going to do that through statistics by building what is called the numerical dynamo covariance matrix. So what is it? It's a matrix that computes many cross-correlations between observed and non-observed variables in the system. And we can do that with a numerical dynamo model by brute force, so to say, simply computing a large number of decorrelated snapshots of the numerical dynamo and performing statistics on that. So in such a way that the probability to obtain a given state vector is given by this formula here. So this is a typical covariance matrix. So how do we read this graph? Here I have plotted the magnetic field coefficients of the poloidal magnetic field at the outer boundary. So this is what is observable. So this is an index that spans all the available spherical harmonics coefficients. And this is, for instance, the axis of the unknown. Here, the poloidal velocity field inside the shell. And what you see is that you can do that as various radii. So here is the core mantle boundary, and here is the inner core boundary. And you see that you get correlations between this and that if you have the same harmonic order, M, but differing harmonic degrees, L. So what this, the translation of this is that you see the influence of the linear part of the equations that govern the system, and especially the Coriolis force, which is a dominant force in the system, that has this property of coupling harmonic degrees together, but not harmonic orders. So the covariance matrix is going to be our main tool for what follows, that is the flow inversion that I want to talk about. So the first step is to look below the surface of the core, where the magnetic field secular variation here is mainly produced by frozen flux advection of the magnetic field itself by a free stream velocity, which I denote by UFS. So this can be formalized in the spectral space like this, with a SV vector, this one, a model matrix which contains the BR coefficients and triple spherical harmonic products, and UFS. And there is also some error because this representation of what happens at the core surface is not perfect. The inverse constrained by a numerical dynamo is a least square inverse that is written here, where you find again the covariance matrix P, the error covariance matrix R, which directly relates to this error, and the model vector. So what we can do is first validate on synthetic data. So this is a typical velocity field from a numerical dynamo, so purely synthetic, and we are going to try to retrieve this structure. So the color scale is the toroidal scalar, which means that if you have blue, it means that it rotates in this direction, and if you have red, it rotates in the opposite direction. So this is what you get when you perform the inversion. So what you immediately see is that you get a fairly good correlation in pattern, but you get missing amplitude. And the reason for that is that you know the secular variation in the magnetic field in the case of the best geomagnetic field models. You know it only up to degree 13, so you have a lot of underparametrization, and you have to account for that. That is to say, if black is the secular variation curve of the magnetic field corresponding to this model, you don't want to fit all of that. You only want to fit the part that you are sure is produced by these coefficients. So the two lines, blue and green, the blue line is the effect I just talked about, the underparametrization, and the green line is the amplitude of magnetic diffusion that is present below the fundamental boundary, and you don't want to fit that either because it's not part of your model. And the red line is the residual, which has to be above those two. So you can determine how much you can fit by a simple iterative procedure that has already been detailed in the literature. So far so good, but these two curves, red and blue, have been determined by something that I know in the synthetics and that I don't know in the model. So I can do another exercise of estimating them. So this is going to be the true Earth situation, and I'm going to talk a little bit later about how I determine the estimations here. So again, this is the result. So again, good correlation in pattern, but missing amplitude. So now, how are we going from those core surface flows that have been extensively studied over the past probably 40 to 50 years? How are we going to go to the full core flow structure? So we are going to borrow some tools from the data assimilation literature. So this is going to be the most complex equation that I present. If I define an observation operator H that takes a velocity vector u to produce only the part UFS that I just determined, I can solve again an inverse problem based on this direct problem here. And the inverse problem is going to be that one. And again, with a similar form, a least square inverse form similar to the previous form I presented. So this solution is quite general and is called the best linear unbiased estimate, blue in short. And this solution can be used to estimate also the deep structure of the magnetic field or of the temperature field. And this is how, for instance, for the magnetic field, I can come to an estimation of the errors that I previously presented. So how well does this work on the synthetics I just presented? This is the typical quality of what you retrieve here versus the reference. And you get morphological agreement between the pattern. So this is the radial velocity in the equatorial plane the patterns of what you retrieve versus what you have in the reference. This is for the azimuthal velocity in the equatorial plane, and this is for an azimuthal cut, a meridional cut, sorry, of the azimuthal velocity. So I don't want to claim that it is perfect at all, but please remember the vast underdetermination of the problem that we are trying to solve. And in that light, I would say that these results are actually quite encouraging, given how little data we can use to do this exercise. So now switching to actual geomagnetic field models. This is, for instance, the flow map that we get in 1990 for the CM4 geomagnetic field model. And this is another inversion that has been performed by Gauthier in 2002 by taking the difference between the Maxsat 1980 and Ørsted 2000, satellites. So you see quite a lot of matching features, but you see that this map adds a lot of new structure compared to this map. So why is it so? So let's summarize what we have. We recover most of the large-scale vortices of this map, but we have added vortices, but it's not purely random added vortices. These are vortices that are equatorially symmetric with respect to the main features of this map. So it's just the higher degree of equatorial symmetry that is constrained by our prior numerical dynamo model that has produced these structures which provide a reasonable fit to the secular variation given the errors that we have estimated. We recover the westward drift in the Atlantic, which is present in those two maps, and we have secondary structures in the Pacific that are not or much weaker, not present or much weaker in these maps. So this is 1990. This is 2001 from Chaos 4. So you see quite a lot of variation. So this is the quality, typical quality of the fit to the secular variation. So again, this is the data, this is the residual, red, and these are the errors that are estimated, the underparametrization error, blue, and diffusion error, green. So these two quantities are normalized misfit to the, so this one is the misfit to the data, and getting a value of 1 simply means that within the errors that you have specified, you have a good fit to the secular variation by your, the flow that you have retrieved. And this is the normalized distance. So NSV is the number of degrees of freedom that you have in your SV. So it's about 100 coefficients in this case. And this is the same, but this is the distance to the time average of the numerical model. So this is how big the departure is between this flow that we have recovered and the time average of the dynamo model. So getting 0.5 here means that, again, you have some missing energy with respect to the typical behavior of the model, and this is, again, due to the fact that you don't have many coefficients to fit, because NSV, in this case, is harmonic coefficients up to degree 13, and NU, we fit the flow up to degree 30 in order to resolve the nonlinear couplings. So this is the structure of the actual velocity. So the velocity in the cylindrical radial direction, this is the equatorial plane. And what you see is that what you have inverted for are mostly convection columns, so the famous Busse columns. So this is Europe, this is India. This big structure here corresponds to this vortex here, and this is America. This is a power spectrum of the velocity field. So you have 4 components: toroidal symmetrical, toroidal asymmetrical with respect to the equator, spheroidal symmetrical, and spheroidal asymmetrical. So what you see, the dashed lines are the average spectra of the prior model. And of course, what is interesting is the departure of our actual flow inversion with respect to the prior. Of special interest is the large-scale coefficients, so L equals 1, 2, where you see that the data has required a much larger content in large scale, and you see it in this pattern here with respect to the typical numerical dynamo. You also see that the data here tend to require in that band, which corresponds to the mode number of the convection, the data tend to require more symmetric with respect to asymmetric component, which means that the data actually tends to want more equator symmetry than the prior itself. So in a way, the data wants columnar convection even more than what the prior numerical model has provided. Okay. This is a cut of the azimuthal velocity in the equatorial plane. So what stands out is a large azimuthal mode number 1 structure, which has been already seen on the previous spectra. And so what is here is a retrograde gyre that has already been proposed. So these are cuts, meridional cuts corresponding to these longitudes here. And this retrograde gyre has already been proposed by Alexandra Pais and Dominique Jo, based on purely quasi-geostrophic inversions of the same problem, secular variation and magnetic field data. So what are quasi-geostrophic inversions? These are inversions that have been performed by assuming that the flow is entirely columnar, purely columnar. So as you see, our inversions which are not constrained in terms of the columnarity of the flow except by the prior, our inversions recover a lot of columnar structure, and it's no surprise after all that we recover the same structure. There is a but. We tend to recover another prograde gyre that kind of spirals with the retrograde gyre, and this is something that tends to be less present in the inversions of Pais and Jo. So this is going to be my last figure for this study of the flows. Based on these flows, you can compute how much the length of day has varied over time in order to see whether you can fit the length of day signal that is thought to arise from the core motion. So there are two curves here mainly. So three curves, the LOD series. So again, the quasi-geostrophic inversions, this is from a study of Nicolas Gillet and co-workers. And what we get from these inversions. So the things that stand out is that none of the two studies here are able to provide a perfect fit of the length of day data. But this is quite typical of this exercise. It's usually quite tough to recover more than a general trend of length of day data. The second thing that stands out is that the quasi-geostrophic core flow inversions tend to over-predict the length of day variation in this period, while the present inversions tend to under-predict them. But both of them recover the decrease, for instance, of the length of day between 1970 and 1990. So this, I think, can be ascribed to the fact that what makes the length of day mostly vary is the amplitude of this retrograde gyre in these inversions, while in the present inversions, you also have the prograde gyre that tends to compensate for the length of day. So where is the truth? Probably between the two, I would say. So the conclusions for this study. So we have used geomagnetic data-based flow inversions in the entire volume of Earth's core, and we have used as a prior an Earth-like numerical dynamo model, and we have observed quite a good model-to-data compatibility as witnessed by the residuals that I have shown. The obtained flows have a columnar and large-scale character, which exceeds that of the prior. So this is interesting because the data tends to adapt on the natural tendency of the model to produce columnar structure and large-scale structure. So I would say this is a a hint that strong hint that supports this type of convection in Earth's core. We also start to see something that is going to be interesting for our future work, a kind of convergence between a full three-dimensional based and quasi-geostrophic dynamical approaches. We have confirmed the presence of a giant eccentric retrograde equatorial gyre, and predicted length of day variations, as I said, are smaller than those induced by purely quasi-geostrophic flows. So now let's move to an outlook, which is the projects that we have at IPGP and at ISTER in Grenoble towards geomagnetic data assimilation. So the goal is to be able to produce interior images of Earth's core, as I just shown, and also to produce forecasts of the system evolution. So I told you earlier that the blue estimation, the best linear unbiased estimate, could be used for estimating all fields in the system, and this is something that we have started to do, for instance, in this study here, where we have a reference field here. So this is again based on synthetic data. We have a reference field here. So the inversion exercise that I've been talking about is here. And here, it's what you get if you let the system evolve through numerical integration of the model, and you progressively add up data to the data in order to refine your estimation. And you see that you can even improve the retrieval of the internal structure here, here, and here by adding up data. So remember that the only thing that is injected in the assimilation is this. So the fact that we retrieve all this is absolutely not spurious. So you can even go on and try to predict the future. So this is an exercise here where we compute the average error of a forecast on an horizon that is varying. So here these are fractions of the advection time of the system, which is roughly 500 years. So this is the typical forecast quality if you have only the poloidal magnetic field as data, if you have the poloidal magnetic field plus secular variation, or if you have the poloidal magnetic field plus secular variation to an even higher degree than previously. And what you see is that in most cases, and for this very simple synthetic system that we have studied in this paper, in most cases the assimilation tends to do better than the linear shoot, except at very short forecast horizons, say 5 years, and when you have very good secular variation data to perform your linear extrapolation. In this case, there is no way the assimilated system, with all the errors that are involved, there is no way that it can beat the linear shoot. But still, what it says is that for typically a long-term, say tens of years range, you can hope to make a better forecast of the magnetic field evolution than a linear shoot. And this is good news, because this long-term range, tens of years to hundreds of years, is exactly the range on which numerical dynamos tend to have less dynamical limitations than the short range, especially because the viscosity in the numerical model being too high, we miss lots of short range, short timescale phenomena. So as a preliminary result here, I have done a long-term forecast of the field over, so what I call long-term is 30 years, starting from data in 1970 and trying to forecast 2000. This is the reference here, and this is what you get by a linear extrapolation, and this is what you get by an assimilation that integrates the flows that I've just shown to you in the previous slide. And what you see is that in this case, you get a significant improvement in your forecast quality. For instance, this equatorial patch of the magnetic field here is grossly overestimated, and much less so here. and same for the magnetic field patches here, which are much better predicted here. So we have an interest window for this type of work in the sense that there are actually probably several workers that might be interested into forecasting the field over these time scales, and I'm especially thinking about people planning satellite missions, for instance, because the time it takes to launch a satellite is really commensurate with this range. So, as an example of interior structure of the magnetic field, this is again a preliminary result where the magnetic field line in 2000 of the previous model that I've shown are represented. So this is the core mantle boundary, this is the inner core boundary. The blobs here are the magnetic field patches, and this is the magnetic field structure, and we are viewing from the southern Atlantic, and we're seeing the southern African vortex winding, for instance, the magnetic field lines here. So I'm concluding with the future program that Alex Fournier is carrying at IPGP. So it's an ANR program which is called AVS GeoMag, which is planned to run from 2011 to 2015. So it's a two-group program, IPGP and Terre. So the goal is to achieve progress in fundamental research in data assimilation in 3D and quasi-geostrophic models. So we are pursuing both approaches, hoping that they will converge, and I'm confident that they will, based on the results that I've shown today. We want to acquire operational forecasting capacity by 2015, in time, hopefully, for the next IGRF, which is the time the geomagnetic community gets together in order to produce an actual model of the geomagnetic field for the given year, and also a forecast for the future. And we also want to acquire a retrospective analysis capacity, which is used data assimilation in order to improve knowledge of the past geomagnetic field. So news on this program will be posted on this website. Thank you.